Okay, so I want to go over some of these vector calculus operations. I'm not going to derive them. I'm not going to really explain all the details behind them. I'm not even going to use them analytically. What I want to do is to show you how you would implement these in Python. And I believe that in doing so, it kind of, I think it gives us a way to kind of see what they are without having to do a lot of the difficult stuff. And the nice thing about Python too is that it allows us to do some of these calculations that would be maybe impossible analytically. Okay, so let's just get started here. So, oh, is my thing a little bit too there? How about that? Okay, so I'm gonna go over each one of these individually. So let's start right here with the idea of a vector field. Now this is a two-dimensional vector field, but I want to show you what a vector field is in case you haven't seen it before. I like to call it an F, vector field F for force, but it could be electric field, it could be magnetic field. But the point is that at every location in space, there's a vector value. So here is the vector field x, y, x hat minus x, y hat, and there's no z component. Now one of the things that I like to do is to write that as a scalar, as ordered pair with these angle brackets. It's one of the common ways of writing a vector instead of writing the x hat and y hat. So I'll do it mostly with the brackets out. But that's a vector field that we're talking about. A lot of these operations either produce vector fields or use vector fields. Okay. So the first operator that we need, a lot of these depend on what I call the del operator. Some people call it Nabla. I don't even know where that comes from, but if you do it in LaTeX, it's called Nabla. Nabla is an operator, much like a derivative. It's like a three-dimensional derivative. You can write it as a vector in Cartesian coordinates. We can also write it in other coordinate systems too, but I'm focusing just on Cartesian coordinates. In Cartesian coordinate, it's the partial with respect to x in the x direction plus the partial with respect to y in the y direction plus the partial with respect to z in the z direction. So you'd write it. I'd write it like this, right? So that's the way I like to write it. So let's use this del operator to take a scalar function and find a vector field, and we call this the gradient. So suppose I have this function. I just completely made this up. So here's my gradient, my function of x, y, and z that returns a single value. It does not return a scalar value. So y z squared times sine of x. I don't even know why I put sine x in there. I just want to make it a little spicy, you know, even though the units wouldn't work, but whatever. So there's my function. So the gradient would just be that del operator operating on that. So I have a vector times a scalar. It's not really times, it's operating, but that just means that I take that partial with respect to x of g in the x direction, the partial with respect to g of g with respect to y in the y direction, the partial with respect to z in the z direction. And I get a vector. So I get three values because each one of those depends on a different thing. If you do that analytically, it's not too bad. The derivative of sine x, a partial of sine x with respect to x, is just cosine x. So then I have the yz term. And in the y direction, I get z squared sine x. And in the z direction, I get 2yz sine x. That's fine. Okay, so how could you do that numerically? So one of the things that you could do is to take a point for g. I'm going to take the point g, 1, 1, 1. So at x equals 1, y equals 1, and z equals 1. And I want to see how that changes as x changes. So this is a plot of g of x for different x values, but y is equal to 1 and z is equal to 1. So I can see how that varies. And that tells me how the partial derivative of g with respect to x. So I can actually do this numerically. I don't need to do this analytically if I know the value of the function. So this is how we would define the partial of g with respect to x. It'd just be that g function plus some little bit amount minus the g function minus some little bit of x amount divided by the length of that interval. So here's my value x at x equals 1. That's from where I'm at. And then I'm going to pick some delta x value, and I'm going to go to the next numerical value, but it could be anything. So let's say it's, I don't even know what it was. Let's say that's 0.2. That must be 0.2. 0.2 to the, so it's going to be x plus 0.2, and that's my new value. I can find the new g function for that, and that can go back down the other way and get a minus delta x, and then I just find the slope between those 2 points, and that is the partial derivative. Okay, but that's just for the x direction. I can do the same thing for the y. Here's my plot of the y function. Actually, this is the same function, but I'm just changing the y value. That blue curve is the leftover from the x. I just wanted to leave it there so you can see what it looks like. So in this case, you can see that the slope here would be constant. It's easier to calculate, but do the same thing. I'd see how does it change in the y direction, and that would be my partial of g with respect to y. And then I could do the same thing for the z direction. Here's the z function. It's more parabolic at x equals 1. I have to know that point, though. I can't just find it everywhere. I'm finding it at the point 1, 1, 1. Okay, so here's how you would do that in Python. Here's my g function. So if I give it a vector value, then I return some scalar value. So that's all this does. I put in a vector and it returns a scalar value. And so this RR, so RR is my temporary vector location. RR.y is the y component of that vector. RR.z is the z component of that vector. This is, yeah, that's right. So this is y z squared times sine of x. That's what that does. Now to get the gradient, I give it another location because I want to find it. That's just a temporary location to RR. ds is how much I want to move back and forth. So the first thing I need to do is dx is how much to move in the x direction, because that is a vector. So I need to move my whole position ds 0, 0, and then back ds 0, 0, and then do the same thing for y and z. So these are directions in the x, y, and z directions. So my x component of my gradient, here I have, it looks just like what I put down in that equation. I have g rr plus dx, and then I call the function g with rr minus dx. And then I divide by twice that interval. And do the same thing for the y direction, do the same thing for the z direction, and then return that vector value. So here's that same example. Here's my temporary vector, and I just call both functions. And if I do that, I get this g, that's a typo right there, that should be a 1. I think you guys can be okay with that. I get 0.8417, that's the value of g at 1, 1, 1. The value of the, I call it the gradient, I don't know what to call it, dl. Oh, the del. It's del g, that's what it is, del g. And I get this vector location. So it kind of tells you the direction of change for that function. Okay, so that's the gradient. Now, this is kind of fun, right? This is that same g function, but what I did was I moved from -1 to 1 in all the x, y, and z directions, and I plotted the value of a vector value for that, an arrow for that vector field. So you can see what it looks like just for fun, and now you can rotate around. And this is in GlowScript VPython. This is what it looks like, just so you can see. I have that same function up above, but I didn't include it down here. So dRt is how much I move in the x, y, and z directions. And then so this is just starting down here. Here's a loop in the z direction. I go from z is -1 to 1, and I make a sphere. I don't even know if I need that sphere. I do have it there. It's very small. And then I make this arrow. And the important thing here is I put the gradient of our, I called it something different here. Okay, that's fine. The gradient of RT there. I do need the scale factor. Scale, I put a scale of 0.7 because that, I'm plotting things in distance. And the function may not work in a distance, so I may have to convert it to a scale. But I do that in the z direction, then I go back and I do the same thing in the y direction. I go back and do the same thing in the x direction. So I make this a three-dimensional grid, and it's kind of fun. Okay, here's a different scalar. This is a vector function. It's a different function. I want to show you it. I made a vector function, x squared y, 2xz, z squared minus 2y. I just made this stuff up just for fun. I wanted to do something that would, we could play with. And I want to calculate the divergence. So the divergence is a way to find a scalar value from a vector field. The gradient is a way to find a vector from a scalar function. Okay, so here's my function. There's my del operator, and the divergence is really just del dot f. So if I take the dot product, I operate the x components together and the y components together in the z, and then add them all up. So I take the partial of the x component of f, which is this x squared y, and I take the partial of that with respect to x, and do the same thing for y, and I do the same thing for z. So in this case, I get 2xy plus 0 plus 2z. But I now want to do this in Python, because that's what I like to do, Python stuff. Okay, so here's how we're going to do this in Python. We're going to pick a value for x, y, and z. I'm going to find the x component of f, and then I'm going to see how f changes with x. And that's a lot like the gradient, right? But the gradient, I only had one function. now I'm going to do the same thing as a gradient, but I'm going to use the x component of the vector field, then the y component, and then the z component. So here's my numerical divergence. I have that same function f. I need that because then I can move it back and forth really easily. And this is all the same as the gradient right there, the ds, the dx, dy, dz. And then just to make it simpler to calculate, I broke it into x, y, and z parts. So that this temp x, notice here that I call the function f of rr plus dx, but then I have a dot x, right? Because this returns, frr returns a vector, but I only want the x component of that vector. I only want this stuff. So that's why this dot x is there. And the same thing there, dot x. And then I divide by 2 ds. And then I add the temp y, temp x, temp z together, and I get my function. So if you do that, the vector at 1, 1, 1, I think this is at 1, 1, 1, the function is 1, 2, negative 1. The divergence is 4. Okay, the next one is the curl. So we have the gradient is finding a vector from a scalar, the divergence is finding a scalar from a vector, and the curl is finding a vector from a vector. So I have the same vector function f, and the only thing different here is I'm going to take the cross product with the del operator and f. And so you can do this a couple of different ways. You can write it as a determinant of a matrix, but I skipped all that stuff. But I get these partial derivatives again, just like I did with the gradient. Now here, you'll notice I have the partial of fz with respect to y, and then minus the partial of fy with respect to z. So it does change things up a little bit. If you do this analytically, I get this function negative 4x, 6, 4z minus 3x. So that's all cool, but let's do it numerically. Oh, and there's I did that out of order. That's my fault. Okay, so here's my curl function. Again, I have that same ds. I can move in the x direction, I can move in the y direction, the z direction to find those partial derivatives. It's the same partial derivatives. But here I have the function f. I'm adding dy. I'm moving in the dy, but I'm looking at how it varies in the z component. So I have a dot z there. Same thing right there. And so I just wrote, if you look at this is that first component, this is the second component, and that's the third component. And then return that vector cfx, and that the c stands for curl fx. I don't know what that means. That's the x component of the curl, I guess. And there you go. So if I take the function 1, the f at 1, 1, 1, I again get 2, 1, 2, negative 1. The curl of that gives me a vector negative 4, 0, 1. So it seems to work. Okay. So that was divergence, gradient, and curl. Now I want to show you the two important things, which are the Stokes theorem and the divergence theorem, and they do depend on two important things. One is the path integral. So imagine I have a path integral. I thought I'd put this as an animation. So we can define work. I'm going to define work as a closed path integral around some loop. So I'm going to take the function f, I'm going to dot it with delta r. Okay, so that did do it. Let's say we start here at this one point and I move a direction delta r, and I know the value of the vector value of f at that location. If my step size is small, then what I can do is just take f dot delta r, which I know the direction of that path, and I can just take the dot product. They're just two vectors. I can take the dot product. And that will be the amount of, I'm calling it work, but it could be any path integral. The work during that one path integral, I'll call it delta W1. And then I do it again. Here's my next step. And then I have a new vector field, which this assumes that same vector field is the same across that whole step size, which is not. But if my step sizes are small, it's mostly true. And that would be work 2, and then work 3, work 4, work 5, and then the total path would be the sum of the works. And this little circle right there means it's a closed path. So normally a lot of the force we use in physics, if you did the work around a closed path, you get 0. Not all of them, but many of them. So that's the path integral. So let's find the path integral for an object. And the first thing we need to do is to move it. I need a path, right? So how do I move an object in a path? Let's pick the path of a circle just because it's a little bit easier. And I need to define that somehow. I need to define the location of that and the direction. I need delta r. So if I parameterize that with some variable theta, then I could say exactly where this point is, the location R, and this is the XZ plane, okay, because so in Python, Y is in this direction, Z is this way. Cosine theta, 0 sine theta. That's my location. So if I change theta, I change the R. And delta R I can get by taking the partial derivative of that with respect to theta, and I get the negative sine theta. Oh, I messed that up. Negative sine theta, 0 cosine theta. And this piece right here just makes sure that each step size adds up to the total area of a circle. So this is the total area around the whole circle, 2 pi r. N is the number of pieces I want to break it into. So I need that to be true too. So here's what that looks like. This is running on Python. There's that. I'm using this vector field, 3xy, 4xz, minus 6x. And as it moves around, I'm showing you the value of the vector field f. And it goes around a complete circle like that, and I can calculate the work. In this case, you can't see it because I'm a poor planner. I thought I'd do something cool. There you go. So the work is, let's see, show me the work. It's 18.8496. Okay, so as I add, and that's 500 step pieces. Okay, I need to move this over here. Okay. Okay. So here's the code for that. So after I define theta, I define d theta. D theta is just 2 pi divided by n, because I need to make sure it breaks into the same pieces. And what I'm going to do is move theta as long as it's less, actually in this case, greater than negative 2 pi, because actually I'm going in the negative theta direction. And that's just for this right-hand rule, which I don't want to get into. So in each step, I need to find the direction of dr and the magnitude. What's that dr vector? It's delta r, but I'm calling it dr. Then I can just draw an arrow for the position of the ball. I don't think I have that. Oh no, that the arrow is at the position of the ball. The axis dr, and then I can calculate fr. The dr you don't see because my steps are too small. I calculate dw. There's a dot product in Python. It's just f dot dr. That's it. And then I take that little d work and I add it to the total work as I go around the thing, and then I move theta and so forth, and I get my value right down there. Okay, the next important thing we need to look at is flux. I like the idea of rain flux. So imagine that I had some sheet of paper and it's raining, and I want to know how much rain hits that piece of paper. Well, this rain flux depends on how fast it's raining. It depends on how big the area is, and also depends on the angle between the normal vector to that area and the direction of the rain. So if you change any of those things, you would change the rain flux. But why do we care about flux? Well, it's in Stokes' theorem, and it's in Green's the divergence theorem too. So we do need to calculate flux. Yes, it's the same thing that you would do in Gauss's law in electricity and magnetism. Okay, so one of the things that we can do with calculating the flux is to use a Monte Carlo method. And this is really just for fun, because if you want to think, if I have some surface, I need to break it up into little pieces, I can do it some orderly manner, but it can get complicated to make sure that the piece sizes are the right size, or I could do it just do it with random values. And that's what I'm going to do right here. So this is actually an example of a Monte Carlo calculation to find the value of pi. Let me see. So here I have a counter n, and then a big counter 100. So this says I'm going to do this 100 times. NC is something that I'm going to show you in just a second. So what I do is I make a random value, a random vector with a random x value and a random y value. So random in Python just returns a value between 0 and 1, and that in the z direction. And if the magnitude of that vector is less than 1, I'm going to count that as part of a circle. And if it's not, I'm going to just count it as just a normal number. And then so I'm going to get some random points inside of a quarter circle and some outside of the circle. The ratio of the number inside to outside should be related to pi, because it's a fourth of an area. So here's 100 points. And so you can see these are all between x equals 0 and 1, y equals 0 and 1. So these red ones are inside the circle, and the cyan ones are outside. So the ratio of the red to the total should be pi over 4. And so if I do that, I get pi is 2 point. You saw that I missed it. I skipped it. It was close to 4, but it's only 100 points. Okay, so we can calculate flux in Python using that same function. What I'm going to do is just to generate some random circles inside of my big circle. Instead of evenly distributing them, I'm just going to randomly distribute them, and hopefully things work out for the best. So this is just a very few circles. The total area of all these circles adds up to the area of the whole circle. And then for each circle, I can assume that the vector field is constant over that circle, and the flux would just be F dot n hat. N hat in this case would be perpendicular to the area, and then multiply by the area of that circle. And then I can get the flux. So that's what I'm doing. Here's the code for that. I start off, I do need to calculate dA, the area of each piece. And so it's just pi r squared divided by the total area. I'm assuming the total area of the circle. And then my number of pieces is just 10 here. This scale just is to display the arrows. I generate a random vector. Now you'll notice something different here. I have 2 times random minus 1. So this gives a number between 2 and 0, 2 times random, and I subtract 1. So now I'm between -1 and 1. So since the circle is centered on the origin, my values can be anywhere between -1 and 1. But I do need to cut off the pieces that are not in the circle, right? So I do want to still check and make sure they're inside the circle. If not, I just throw them away. I don't care about that. I'm going to do it again. I don't count it as n. I only increase n if it's inside the circle. And then right here in line 27, I make a cylinder to represent that piece of area. I draw an arrow. This arrow is F. And then n hat is just, in this case, it's a flat circle, so n hat's in the y direction. I calculate the flux as the dot product, and then I add to the total flux, and that's that. We can use this with Stokes' theorem, which my animation got a little messed up. And I'm not sure. Oh, this is from before. That's the work. So here I have a path integral. Stokes' theorem relates a path integral to a flux. But in this case, it's the flux of the curl of the function. So I have to take that flux, that function f, take the curl, and then find the flux over the same area. So here is the function f. We already said that. There's the curl of my function f. I'm going to do the flux of this and the path integral of that. Now, the important thing is that the area for the flux it has to be the same bounded by the same area as the closed path. So in this case, I have that circle as my closed path, and I have a flat circle area as my flux, and that's fine. But it doesn't have to be that. I could do whatever I want. Okay, I don't remember what I'm doing here. Okay, so this is much larger pieces for the flux. The work is 18.8481, and the flux is 18.8496. So just show you both sides that Stokes' theorem is true, right? I integrate the path integral around there, I calculate the flux, and they're pretty much the same. Of course, they're not exactly the same. One, I'm using some random values here, so every time you run it, it's going to be different. And two, I did only break this into something like 100 pieces. So you can make this better, but it's good enough, and I think it really helps you understand what's going on. Now, imagine trying to break this into squares and evenly distributing those squares around the circle. It's not easy. You could do polar coordinates, yes, but then at that point, it's harder to draw. So I like doing this way. Okay, let's do another bounded surface by that same circle, a hemisphere. So how do we make a hemisphere with Monte Carlo? Well, in this case, I want to start with a cube of points that's -1 to 1 in all directions. And what I want to start with that because I know it's uniformly distributed. And then I can just cut away everything that I don't want. I'm going to cut away the negative y values because I want it only in the positive values. And then I'm going to find the r values between some r plus dr and r minus dr. So I need to have some thickness. I can't just say if r is equal to this, right? I could say as r is less than that, but then it'd be a solid sphere. I only want the shell. So that's what that r minus dr and r plus dr do. That helps give me a shell. So this is the 2 by 2 by 2 value of points. That's 1,000 points in Python. Really easy to make. I did my order wrong here, but you can see what's going on. I just have that 2 times random minus 1 for the x, y, and z coordinates, and I just count up all the points, and that's a sphere. That's 1,000 points. I did this backwards again too. Okay, so here is those same points in a sphere, in a hemisphere. So I cut off, I have here if the magnitude of that is greater than r minus dr but less than r plus dr, and if the y value is greater than 0. So this is 1,000 points in a hemisphere. But those are just spheres. Okay, so what I'm going to do is to use cylinders instead of spheres because I can place those as little tiny areas. I need to set the area of each circle in that hemisphere equal to the total area of the hemisphere divided by the number of points. And then I need to define in hat, right? Here's something that's different because as I move around the hemisphere, all the in hats are in different directions. In this case, since the hemisphere is centered on the origin, the r vector locating each piece is the same as the unit vector that's perpendicular to the sphere. I don't know why it's doing that. Okay, well, here's my hemisphere with my circles. This is what 50 spheres, and each one of those yellow vectors represents the in hat, and that's kind of cool. I like it. And of course, they're not perfectly evenly distributed because it's random, and that's fine. So here is a much larger number of points. I can't remember how many points these are. I didn't draw the arrows, but I calculated the flux. It's the same work around that path, but now I have a flux over this hemisphere, and you see it still works. Whether we have a flat circle or a hemisphere, it still works. But wait, we can do another one. So what about a cylinder that has a top on it, right? But it's still bounded by that same path. So how would you do a cylinder? Again, I would make a random box of points, and I would cut away everything I don't want. In this case, I need to define this vector in the xz plane because I'm cutting that kind of circle, not in a hemisphere. And so there's my code hidden because I messed up on my slide, but I think you get the picture from that. And so here's all those points. I had to put a top on it too, which is similar to that circle down at the bottom. But it's a cylinder with a side and a top, but not a bottom, right? Because it's just a surface bounded by that curve. And you can see that I do indeed get the same flux. Okay, all three of those have, this actually has all three. It has the circle on the bottom, the hemisphere, and the cylinder with the top missing. And it works. So that's Stokes' theorem. Okay, here's the divergence theorem. So in this case, I have a volume. This is a volume integral of the divergence bounded by a closed surface integral. So that's my volume. That's my surface integral right there. And they have to be bounded. So let's use the vector f, x squared y, 2xz, z squared minus 2. I used that before. I take the divergence of that, and I get a scalar function, but then I need to integrate over the volume. So we already know how to do the flux. We need to do a volume integral here. So the volume integral is actually pretty easy. Instead of saying I want to generate some spheres that are in a thin slice, I just have the whole thing filled. So I'll say if the radius is greater than some value r, throw it away. If not, keep it, and then make the size of each cylinder such that when I add up, not cylinder, these are spheres, the volume of all the spheres added up is equal to the volume of the whole thing. So now each one of those is a little volume element. And I can calculate the volume integral by taking the value of the vector divergence at that location times the volume of each sphere. And I have to do that, right? Because the divergence changes as you move around in those different spaces. So I need to do that. And then I can just find the volume element, multiply by the divergence, and then add up all those pieces, and I get the volume integral. And that's for 1,000 points. And then if I put those two together, I have the flux, which I've already done. This is not the flux of the curl. This is the flux of the function, f dot n hat dr. But it's the same thing. I just don't take the curl. And you can see that I get, they're both mostly the same. In fact, in this case, with the function I picked, they should both be 0. So that's why it looks a little bit different. But q is the volume integral, flux is the flux, and they're both close to 0. I could actually do this with a different volume. This is a cube, not centered on the origin. So each of these faces is pretty easy to make because all the unit vectors for these circles are the same direction, right? X hat, Y hat, or Z hat. I just need to make those vectors, put them in the right location. But once I do that, I can calculate f dot n hat dr, dA for each of those, and then add them all up. And then I can do a volume integral again with the spheres. I've already shown you 1,000 spheres in a cube. And this looks a lot better because it's not 0. So there you go. So that's the gradient, the divergence, the curl, Stokes' theorem, and the divergence theorem. And that is that. And I hope you find that useful. I'll include some links down below to some of my other videos about these same math vector functions, and maybe you can find them useful. But hope hopefully you like that. I had fun, so.